Okay, Bobcats, here is Chemistry 2341. We're going to continue on with NMR spectroscopy in Chapter 9, and today we're going to talk about carbon-13 NMR. Okay, so carbon-13 NMR is typically easier to analyze than our proton spectrum because we do not have splitting and we don't care about the intensity of the peaks. So what we're really looking for is the number of peaks and the chemical shift. So each type of carbon atom will appear as a single peak. So in this example here, we have acetic acid, and we have a carbon with 3 hydrogens on it and a carbonyl. And so we have two different types of carbons, and so they appear one peak for the carbonyl and one peak for the methyl group. Okay. So let's talk a little bit about splitting and why it doesn't happen in carbon NMR. In carbon NMR, we don't see that because carbon-13 is actually a fairly low abundance in nature. In nature, we see carbon-13 in about 1.3%. Therefore, the likelihood of having two carbon-13 atoms next to each other to cause splitting is very, very low. So we really don't see that splitting at all. In addition, carbon-13 can be split by hydrogen, but most of the time, we actually do a program that decouples the proton and carbon by pulsing at a different frequency, such that the protons don't split the protons do not split the carbon-13, and therefore all the different types of atoms in all the different types of carbons in a compound appear as a single peak. Okay, so what that means is that all we care about in carbon-13 NMR is the number of signals observed, and therefore we get one signal for each type of non-equivalent carbon, and the shifts of those signals. Okay, so let's look at that shift right there. So similarly to proton NMR, we have our shift range in ppm, but in carbon-13, our absorbance are over a much broader range. We start at 0 with our tetramethyl silane compound, and we go all the way up to approximately 220 ppm for things with carbonyls on it, okay? So the chemical shifts are analogous to the same types of shifts we see in proton NMR. So we have aliphatics being the highest upfield and our carbonyls being the most downfield of our system. Okay, so let's look at a table of those. So the first thing we'll notice is our sp3 hybridized carbons right here are going to be our lowest shift of between 0 and 50 ppm. As we start adding electronegative atoms, that shifts up from that 50 range into the 60 to 90 range. By adding a triple bond or a double bond, we're jumping again into the 60 to 100 range. Aromatic rings, because we have those conjugated double bonds, they typically lie in the 100 to 170 range, just like the other double bonds. Having a triple bond with an electronegative atom gives us a range of approximately 120 to 130. Having a carbonyl with an electron donating group, like an ester or a nitrogen here for an amide, we get in the 150 to 185 range right here. Now, if we have a carbonyl with no electron donating group on it at all, like an aldehyde or a ketone, those are our highest shifts of between 180 to 220 ppm, okay? So, just like in proton NMR, the number of carbon-13 signals is equivalent to the number of different types of carbon atoms in the molecule, okay? And because they're not split, it makes it easier to see them, okay? So the intensity, unfortunately, is not proportional to the number of absorbing carbons. We do not tend to integrate carbon-13 NMR unless you're running a specific quantitative experiment. So most of the time, we're just looking at the number of peaks and the shifts of the peak. Okay, now let's talk about equivalent carbons, okay? Just like before, we're looking at the electronic structure near that carbon. In the case here, we have a carbon with hydrogens on it, and it's bonded to an oxygen, and therefore that's equivalent to this other carbon with hydrogens on it, bonded to that same oxygen. Therefore, that has equivalent carbons, therefore that gives us one NMR signal, okay? So now let's look at this one. We have this carbon here that's bonded to a chlorine and a carbon. So that's different in nature than this carbon here bonded to hydrogens and just another carbon. So that means we have two different types of carbons, and we should see two signals in the carbon NMR. Okay, let's take this nice ester for a difference here. And so we have a carbon bonded to an oxygen, which is going to give us one signal. We have this methyl group bonded to a carbonyl, which is going to give us our second signal. And then the carbonyl carbon itself, even though we don't see it in proton NMR because there's no hydrogen on it, we have a different carbon here, so that will give rise to our third NMR signal in carbon NMR. Okay, so let's see what that looks like here. So in something simple like propanol here, we have our carbon bonded next to our electronegative species. And so that's going to be the furthest downfield we see. In fact, we see this carbon number 3 right here, up in that 50 to 70 ppm range. That's very common for alcohols, the carbon that has the OH on it. Okay, now the one we'll see next is the one that's closest to that oxygen, but still has a carbon bonded to it. So that's going to be shifted partially downfield, but not as far downfield as the one that actually has the oxygen on it. And our last one is going to be the most hydrocarbon-like because it has to go through multiple carbon bonds before it sees that oxygen. Therefore, it's going to be shifted almost very little from 10 ppm, and so it has the least amount of shift possible. And so we have a total of 1, 2, 3 types of carbons, and we've identified which carbon they are by how close they are to that electronegative element. And that is the simple part of carbon NMR, because we only have to worry about the number of peaks and their chemical shift.